Okay. The first thing we're going to do is what we're going to look at is we're going to talk about domain restrictions. So take a minute and just read through this little section right here. Okay. All right. So there are some things that I know if my BC students know this because I had never taught this to them. And we did polar really fast at the end. I taught them enough about polar to be able to do a polar question on the AP test from a calculus perspective. Okay. But this does come up in BC next year. Okay. And I think us just doing this and having a better understanding of how the polar graphs act actually helps. Okay. So we're going to kind of hit the highlights. We're not going to do every example on here today. I'm going to try to get through the end of it though, because the last two examples are actually really relevant to what we do in BC next year. Okay. So the first one is the domain restrictions for completing one cycle of a polar graph. Okay. Then we're going to look at negative R values. And those mostly help us with the limacons, okay, limacons, however you want to say it. And then the finding the points of intersection, those are the ones we actually need that for BC next year. Okay. So I know we did not do a good job of graphing rectangular wise our trig last year. Okay. I don't remember if we even did a Desmos activity. We might have. Usually that's how I do it. I throw in a Desmos activity sometime when I'm not in class. So that is what a sine wave looks like. It's shifted a little bit. Okay. Because this graph is shifted. It's probably shifted up one and it's probably stretched a little bit because there's a 2 in front. But that's basically what a sine wave looks like. And a sine wave is going to, the domain on a sine wave, or the first interval of the sine wave is going to go from 0 to 2 pi. Okay. And then it's going to repeat. Let's just look really quick at the sine wave here. Oh, that's not what I wanted. Desmos. All right. So y equals sine x. Sine x, not x. Okay. So do you see how it starts here at 0 and then it repeats at 2 pi? Okay. And then it's going to start over and it keeps doing that repeat. That's basically one revolution around our unit circle. Okay. So we call those functions that do that with our periodic. Okay. It had that. And that's what we consider the length of a period. It's from 0 to 2 pi. Okay. And it keeps going and going. The next one's going to go from 2 pi to 4 pi. Right. So what they're talking about here is how do we know something is negative, okay, in this graph here that we've got. So let's look at this. So what we're going to do is we're going to just try to figure out how this corresponds to this graph right here, because this is the graph that it looks like polar. This is if we graphed it rectangular. This is if we graphed it polar, okay? So let's try to do this a little bit smart. Let's put this function in. But instead of doing, well, we can do r's and thetas. It's in x's and y's. Let's put the as in y equals 1 plus 2 sine x. Actually, let's not do y. Let's do f of x. So I'm going to show you a nice little trick on Desmos since we're using Desmos today. F of x equals 1 plus sine x, okay, which is the rectangular graph we just saw down there. Oh, maybe not. Let me double check that. Did I do it right? 1 plus 2 sine x. I wasn't right. It's 2 sine x. Didn't look quite right. Okay. So now that is the graph that we've got going from 1 or 0. That's 11 pi over 6. It's probably repeating somewhere right in here, right? It starts the repeat over right there, which is probably 2 pi. It's saying in decimal, but that's 2 pi. All right. So to get our value, instead of having to keep typing in and replacing here, I'm just going to do f of, my first number was 0, and I'm going to get a decimal point. Okay, so f of 0. You got a 1. And then I could do f of, I think it was pi over 6. Okay, and I got a 2. And then f of pi over 4. And I get that decimal point. So here's what I want you to do. I'm going to give you 3 minutes right now. I want you to go through and fill in the table. Okay? And then we're going to check it against my table. So everybody go through, find out, and you don't have to keep going in line. You could just delete over the top, right? Okay. So I'm going to give you 3 minutes right now to fill in all of the table. Okay. Make sure you write them down. I'll give you about 1 more minute. Okay. Okay, I'm going to show you the values I got. Mine are only 2 decimal places because I was borrowing an answer key and they only went 2 decimal places. So make sure you probably have 3, and that's perfectly good. That's how I would prefer it. Okay, so double check your values, see if we match. Okay, I'll give you about 20 more seconds to check. All right. The idea behind this is that there is a relationship between what the graph looks like rectangular, okay, and what the graph looks like polar down here, okay? Really what's happening is that these are the thetas and these are the R values, right? They kind of get reversed. I mean, we normally draw the table the other way when we're looking at polar, okay? So if I was thinking about, I'm in particularly curious about these values in here, the negative ones, okay? So let's just see where that would graph on the polar graph. So this is saying I'm at, let's see, let's go to 4 pi over 3 because that one we actually have a line for. If 4 pi over 3 is this line right here, right? But it says I got to go negative, so that means I have to pop back across, which means I am right there on the graph, okay? And then 3 pi over 2 says I'm at negative 1. So this is 3 pi over 2 here. I pop back, I'm at negative 1. 5 pi over 3 is this line right here. And then I pop back and I'm here. So in this particular picture, what are the negative values getting us? Yeah, it gets us that inner loop, which we kind of started hinting at that the other day when we were drawing these. There was something weird that was going on because we kept getting a negative, and then we would just draw it negative, and even though both the values were negative. So what's really going on is if you get a negative answer, it means that that's really that inner loop piece. Okay, that's what's going on there. And if you look, if we had the graph of the rectangular version of it, all we would have to do is know that these values right here underneath the y-axis are the inner loop values. Okay. So that's just kind of an interesting observation that we know if it goes negative, it's creating that loop. Okay. All right. Let's look at domain restrictions. We're going to probably do about 4 of these. Okay. And this is, domain is always tough. Okay. I don't know what it is about X. I think X and Y domain is not so bad. But sometimes we look at some of these things that are a little bit different, and the domain on these is tough. So we're gonna use Desmos to help us understand it a little bit. But we're gonna always start with finding our zeros. Okay. So we're supposed to determine the domain restrictions for sketching the polar curve through one cycle, meaning it only goes around it once. We know because polar and unit circle, we can keep going around it infinite number of times. Okay. Because it just adds another period to it. But we're going to use the auxiliary graph of the corresponding function to assist you if you want. We're going to actually just use, we're going to find zeros and use our, whatchamacallit, and use Desmos to help us kind of see where that cuts off. Okay. So I'm going to just start by taking this guy and setting it equal to 0. So 3 plus 3 cosine of theta equals 0. Okay. I have to get cosine theta by itself. All right, so how do I move the 3 to the other side? Subtract it, and then what am I going to do to move the other 3? Divide it, so cosine of theta equals -1. So we are now back to solving a trig equation, so we got to reverse our unit circle. It's been a while since we've done that. So we got to find the angle measure, okay? So I need to think about where is my cosine. I'm going to do it over here to the side. Where's my cosine equal to -1? So is that an x value or a y value? X value. So I think the only one is right there, right? What's my radian measure right there? Pi. So I know that that happens at pi, but it also happens if I'm here at pi, it happens here. And then it happens at pi again, right? And then at pi again and again. It happens every time I loop around the unit circle. So technically that happens every time I go 2 pi n around the unit circle. Okay. All right. So my zeros, okay, could be if I'm going to substitute, try to find everywhere that is looping around. Okay. So if I put in that I have zero revolutions around, I'm at pi. If I put a 1 in for that n, now I'm at 1 pi plus 2 pi would be 3 pi would be another 0, which means I'm outside of 1 revolution around. So I'm going to look at my domain. So this is trying to help me assist what kind of narrow down where it is. I know that it's probably going to start at 0. Okay. And I know it's probably not going to end at pi. It's either going to end at pi or probably 2 pi, because 3 pi we know is going to go around too many times. So here's where I go to my Desmos. So everybody get Desmos open. We're going to type this in and we're going to go polar. And then we're going to mess with the domain, or we're going to mess with the domain restrictions on it. So r equals 3 plus 3 cosine theta. Okay, so there's my graph. I'm going to switch this over to the polar mode here. Okay. Notice underneath here, it's telling me right now it's going 0 to 2 pi. Okay. So it's saying that right now it's only going around 1 time, or it's going maybe one revolution around. Let's just switch that to 0 to pi. You see how it only graphed half of it? So if I did 0 to 2 pi, it goes more. Okay. If I tried to do 3 pi, we probably wouldn't see much. You can't even tell, right? Here's what I would do to test that theory out. 0 to 2 pi. Okay. I would take this and copy it and paste it and see what happens if I go like 3 pi to 4 pi. So see how it only graphs this chunk of it, but it's overlapping what we already had, right? So I know that 2 pi, so this domain has to be 0 to 2 pi because that makes it the shape go around one time, okay? All right. So I know I'm going to go 0 to 2 pi. And you guys, domain restrictions are hard. I had to study this morning, okay? Because this is not easy stuff, all right? And it's been many, if I've ever taught it, years since I've taught it or dealt with it. So I'm doing my best here this morning. So the next, we're going to go ahead and set the next one equal to 0. So let's try the one with the rose curve here. So setting it equal to 0, I'm going to move the 4 over, so that gives me sine of 5 theta equals 0. Okay. So I need is sine the x value or the y value? Y value. Where are my y values equal to 0? What radian measures? I heard it 0 and where? Pi, right? So 0 and pi. So I know and remember with this multiple angle thing in here, we go 5 theta equals 0 and 5 theta equals pi. But there's a catch. We have to get all of the revolutions around, and every time this is going to happen. So each revolution happens in 2 pi. So we write a 2 pi n after it. That's going to take for the fact that maybe this loop, we need to do a little bit more. Okay. All right. I've got to get pi, or the theta by itself. How would I move these 5s to the other side? Divide. So I'm going to divide, and I normally don't write this out in a calculus class, right? Normally you don't see me doing this part. I'm going to divide everything by 5, okay, including the pi n thing. So we've got theta equals 0 plus 2 pi over 5n. And theta equals pi over 5 plus 2 pi over 5n. Okay, I'm going to see how many times I really should get back to this, because think about how we draw this, right? I'm going to start here and I'm going to loop there and I'm going to touch 0, right? And I'm going to start here and I'm going to loop here and I'm going to touch 0 again. So that's 2 zeros. I'm going to touch 0 again, 3 zeros, 4 zeros, 5. So I need like 5 or 6 values that I'm going to get off of trying to find these zeros to look at my domain, okay? So let's see if I'm falling in, what I'm falling in between, okay? So my first 0, and remember, I keep plugging in n. So what we're going to do here is we're going to plug in n, okay? I'm just going to start with 0, and then I'm going to go to 1 and 2 and 3 until I hit 2 pi. In our world right here in 5s, 2 pi, well, let's see what happens, okay? I think 2 pi, so until we hit 2 pi, okay? So theta equals, I'm putting in a 0, I would get 0. I'm putting a 1 into this, I get 2 pi over 5. I'm still underneath 2 pi, right? I put in a 2, I would get 4 pi over 5. All right, let's see what happens on this one here. So I did a few here. If I need to, I can always go more, but let's see if we get a few off of this one. 0 equals, let's see, I have 1 pi. When I put 0 into that, I would just get pi over 5. When I put 1 into this, that gives me 2 pi, plus 1 pi would be 3 pi over 5. I put 2 into this. 2 times 2 is 4, plus 1 pi is 5 pi over 5. So what I needed was I needed to hit 0. Needed to cross 0 5 to 6 times, okay, to get that rose curve, right? Technically, 5 pi over 5 is what number? pi. So maybe my domain, and I finish it at pi versus going all the way to 2 pi. Okay, so let's see what happens when we graph it and mess with the domain there. Okay, so this is how to do this if you don't have like a calculator in front of you. It's kind of a good way to kind of guess a little bit, or not guess, but try to figure it out. So let's put that function in. It was r equals 4 sine of 5 theta. 5 theta. Okay. Oh, look at it. It Desmos is too smart for us. Look at what it automatically did. It said 0 to pi, right? Let's see what happens if I go pi to 2 pi. It gives me the whole thing again, right? So I know that my original domain has to go 0 to pi. So we were right. It crossed once we crossed like that pi times that last one, that 6th time, we were done with the curve. If I went less than that, like pi over 2, I don't have the whole thing. Okay. All right. Let's try another one. Okay. So, the domain on that one was 0 less than theta less than pi. Okay. Let's look at C and see if we can get that one. I do want to type 55. What do I want to do? Probably just going to do C. Okay. Let's do D. Okay. I'm looking at with the complicatedness of it. This one here, you guys, this is going to be like a nice to know. I'm not going to put this on the quiz. Okay. Because I know that it's harder to understand. Okay. But I want you to at least have seen it. Okay. Because I think it'll make it easier for you next year. All right. So here we're going to set it. Our rule of the game is, what do we set it equal to? 0. Okay. So, and again, we're trying to figure out what's our domain on this thing. All right. I divide by 4, so I have cosine of theta equals 0. Okay, so where is cosine equal to 0? Oh, not that these two spots, is it? Where's cosine equal to 0? What radian measures? Pi over 2 and 3 pi over 2. And notice, so far we haven't had to go out of side of the quadrant axes on these, or the quadrant angles on the unit circle here. All right, so I know that theta equals either pi over 2 or 3 pi over 2, or any revolution of them, right? So that's why I add that 2 pi n. Okay, let's see if we can get, or so let's see what values we end up getting on this one, okay? And I'm going to test them. And really, I should start at 0, right? And then I'm going to come back to it one time, right? I'm going to end at 0. So really, I need 2 values, okay? We're going to go more than 2 just to see what happens, okay? So if I put in a 0 into that, I would get pi over 2. If I put a 1 into this, that would be like, let me add an extra line in there so you can see me do the work really quick. So pi over 2. All right, if I put in a 1, I would have pi over 2 plus 2 pi, or, oops, wrong way. 4 over 2 pi. So that would be 5 pi over 2, which is bigger than the unit circle, isn't it? So that one's too big. Let's try this one here, okay? If I put in a 0 for the n, I would end up with 3 pi over 2. If I put a 1 in for the n, I get 2 pi, or 4 pi over 2, which would be 7 pi over 2, which again is more than 1 revolution around the unit circle. So it's likely that this is between, it's either going to be between 0 and pi maybe, or 0 and 2 pi. So this one might be too much. Okay, so let's see what happens when we put it into Desmos. I think it's 0 to pi. Because we started 0, one of them, and then we loop around one time, and so we'd land at pi over 2. All right, let's see. R equals 4 cosine of theta. All right, look at what they said. So they're saying 0 pi gets us 1 revolution. If I do 2 pi, you're not going to see any change, right? If I do 0 to pi over 2, I only get half. So 0 to pi on this one. Okay, let's look down at the next. We're going to go to the next section, okay? Actually, I don't know if I want to do that section. Let's see what we got. We've got 20 minutes. We've kind of already talked about the next section because this is the same example as example 1, and it's talking about where the R values are negative, which we've already really done that. Let's come back to that if we've got time. I really want to make sure we do example 5 and 6 because we need these two for next year. Okay, it really just gives us the inner loop thing again. So let's make sure we understand these two here. Okay, these are the important ones. So this is why I kept doing this lesson. So the intersections of polar graphs. Points of intersection can be found algebraically. There also can be common points that are not part of the solution set. So just looking at those two graphs, how many times do you think they intersect? What does it look like in the picture? Kind of looks like 3, right? So I've got this one, and this one, right? Because I've got a circle and I've got the limacon with the inner loop, right? So it looks like 3. So we're going to try to see how many it really is here, okay? So remember, for it to actually be intersections, the actual y value has to come out to be the same, okay? So I'm going to start by trying to figure out where they intersect. When I figure out intersection points, I set the two equations equal to each other, right? So let's set these two equations equal to each other. So 1 minus 2 cosine theta equals 1. And we're going to solve for theta. Okay. All right. So I've got negative 2 cosine theta equals, when I subtract 1, what do I get? 0. Good. And I'm going to divide by 2. What do I get? 0 again, right? Okay, we're back to good old unit circle. Oh, nope, it's up here, right? 0, 1, and 0, negative 1. So what radian measures does cosine equal 0? What's this one at the top? Pi over 2 is the one at the bottom. Okay, so that's basically saying my graphs intersect at pi over 2 and 3 pi over 2. Isn't that one of the intersection points? There's my pi over 2 intersection point right there, right? And this is my 3 pi over 2 intersection point. Well, that's kind of weird. There was supposed to be a third one. I wonder what happened. Okay. So let's see if we can figure out what happened with it. And let's actually we're going to start by just showing the 2 points that intersect. So we know that, go ahead and put this guy into Desmos, okay? And I'm going to do it a little bit different. I'm going to say R parentheses of theta equals 1. I'm doing that on purpose so I don't have to keep typing in R2 cosine theta. All right, so I'm going to go R of, and then I'm just going to type in the pi over 2 just to check and see what it is. So we notice that our answer is 1, right? Which is what we expected, right? And then we're going to do R of 3 pi over 2, which is also 1. So that was the answer that we were expecting, okay? Because they both went 1 ring out. Aren't my answers to this one, no matter what theta I put in, always 1? So we know that on both graphs, the point 1 pi over 2 exists, and the point 1 3 pi over 2 exists on both graphs. So those are the points of intersection. Okay, but there's still this other weird point over here. If I were to read that point off the graph, what is the radian measure right here? Where is that on the unit circle? What radian? Pi. Okay, so we know that pi is the radian measure. How many rings is it out? 1. Okay, so let's try putting pi into this equation here and see what happens. Okay, I should be getting a 1, right? That's what we just said. It's got to be 1. All right, so I'm going to go into this equation that we just had. Same equation. I'm going to put in pi. Did I get 1? No. Look at what I got. 1 ring, 2 ring, 3 rings. It's right here. Okay. So this is what we call having a point in common, because what it's saying is the circle hits right there, okay, at the same time that the limacon hits out here. Okay, when those both hit at pi, they both are one's here and one's here. My limacon comes back in again and then loops around there and before it hits that point there. So they're not hitting it at the same time. Okay, so this is just a point in common. Okay, if we did, let's just write this down so you have it. I'm going to call this one r sub 1. So because r sub 1 of pi equals 3. And r sub 2 of pi, this could be r sub 2, equals 1. So they're not equal. All right, let's look at example 6, and then we're going to call it good. Okay. You guys have been really... You're all tired from that amazing concert last night, right? This is why I got no grading done last night. If you didn't get to hear the concert, they did an amazing job. My husband was very impressed with... is it Symphonics, our highest one, right? Eventually, I'll learn all the names. He was very impressed with Symphonics. So, and my son Andy perked up when percussion got on. So he was kind of bored until then. And then John gets recognized every time because my kids always ask, "Is he the mouse?" Because he played the mouse in the play in the fall. Yes. And then it was Priscilliana. Mikey kept asking, I don't know who was Mikey or Davey. One of the two was asking who Priscilliana was. So. All right. Let's look at this one. What if I want to find points of intersection? What do I need to do with the two equations? Set them equal to each other. How many does it look like there are in the picture? 3, but we kind of know that probably isn't true, right? But given what we just did in the last problem. Okay. All right, so let's look at setting them equal to each other and seeing if we can find this by hand. Okay. Now, the good news is sometimes on the AP exam, they tell us the points of intersection. So let's think about where this would go. I'm just going to preview this. What they might ask us to do on the AP test next year is, hey, find that area. Those points of intersection become your upper and your lower bounds. Okay, so that's why this has purpose, right? Because we've got to be able to do that for next year. Okay. We already see, you guys already know more calculus than you think you do going into next year. See, it makes it next year so much easier because you already know derivatives and integrals. All right, let's take a look. So I'm going to take this sine to the other side. So I have 3 sine minus 1 sine is going to give me what? 2 sine theta equals 1. All right, let's see, sine theta equals 1/2. Uh-oh, it's been a long time since we've done something other than quadrant angles, right? Okay, is sine the x or the y? The y. So I need to figure out where my y's are equal to 1/2. I know that's 0, 1, so my first one here that would be a 1/2. What radian measures right here? Pi over 6. And we know that enough about the unit circle that shouldn't it mirror it on this side? So -1, 0, the 1/2 should be right there. What radian measures this one? Think about this. If this is 6 pi over 6, and I have to back up 1, 5 pi over 6. So I know that my intersection points are at pi over 6 and 5 pi over 6. How many rings out are they? Just look at the picture. Oh, it's a little bit more than something. It isn't on exactly, is it? Yeah, we'd have to go in and we'd have to do our whatchamacallit. We'd have to find the decimal point. So it'd be something pi over 6 and something 5 pi over 6. So what's this thing right here? Where does it look like it's crossing at? It looks kind of like 0, 0, right? And we just calculated that it's not one of the intersection points, so that would mean that we have a common point at 0, 0. All right, let's use our calculator really quick and figure out what these values are. So we're going to put it, does it matter which function I put it into? Shouldn't they be the same? Okay, so well, actually, let's try them both. So we're going to put both of those in and try pi over 6 into both of them, just to prove to ourselves that they are the same value there. Because we didn't really see that the last time because the other one was just 1. So let's do this really quick. All right, so let's do r of, I'm going to go theta. I'm going to let me do subscript. Oh, r sub 1 of theta, perfect. To do a subscript, you guys, all I did was I hit shift and the underscore key next to the 0, and that gives me, so I can do 2 different equations. R sub 1 of theta equals 3 sine theta. Theta. Oh, what happened? 3 sine theta. Why didn't it do it in polar? Oh, because I did the subscript. Never mind, don't do the subscript. There we go, now it's in polar. All right, so r of pi over 6. This might not work out like I wanted to. I got 1.5. Let's see if I do another r of theta, it'll let me do 2 r of thetas. R of theta equals, and then we want the 1 plus sine of theta. Oh, see, now it doesn't like that because I've got too many, right? Okay, so we said that this one was 1.5, right? Let's cross that out. Oh, look at what happened when I took that away. I got 1.5 again for this r. Okay, so both of them are 1.5. So, and then this should mirror that on the other side, right? 1.5. Okay, that's where I'm going to stop. I will put some work out there, okay? Did you notice I said we're going to do a quiz on Tuesday? Okay, so this stuff here, nice to know, not on the quiz, right? We did it, so we understood a little bit about domain, not on the quiz. Remember what we were doing in Desmos, GimKit yesterday? Easy stuff on the quiz, okay? The only thing that was on there that was a little bit more challenging was converting from polar to rectangular and rectangular to polar. So you're going to have a little bit of that. I will have a review out there no later than Monday. If I get it out over the weekend, I will send you a text message, okay? So you'll have Monday in class to review. Tuesday we'll take the quiz. Hopefully you don't have to re-quiz it, okay? So I'll get a 3.5 or better, okay? And I should have grades. I have 2 more things to put into your grades, and then the letter grade should show up, okay? So you should know at least what letter grade you're at, okay? And permission slips by when? Monday. Oh, and did you guys see on Monday?